feel the vibe.
What's up, guys? Welcome back to another Algebra 2 lesson here with Mr. Gaines as we continue our work with exponential and logarithmic functions. Today we are going to focus on some applications of these types of equations. Exponential and logarithmic functions you guys are going to find are probably some of the most useful tools that we have from Algebra 2 outside of the classroom, and we're going to see some instances in which we can apply them. First, we're going to focus on exponential growth and decay type situations. And so what we're going to start with is an equation. So this equation here works for the majority of exponential growth and decay situations. So as we break this down, Q of t is going to stand for the quantity over time. So this is going to give us a function where quantity is in respect to time. Q sub 0 is going to be the initial quantity or the initial amount. R is going to stand for the rate, the growth or decay rate. And T is time. So this equation, Q sub t, or Q of t, is equal to Q sub 0 times the quantity 1 plus or minus R to the t power. It gives us an exponential and growth decay model that's going to apply to a variety of different situations. So this type of exponential growth or decay can represent situations in which the growth or decay is occurring as a percentage of a previous number. So for example, let's take a look at problem number 1, where it says, which of the following gives the savings in an account if $250 were invested at an interest rate of 3% per year? So what we see here is that we are starting by putting $250 into the account. So Q sub t, or Q of t as we have it written above, is going to be equal to 250 times an increasing rate. So when we increase, we are going to add the percentage to 1. So this would be 1 plus, sorry about that, the 3% rate in which we are going to be accruing interest on a yearly basis. So this would be 250 times 1 plus 0.03 to the t power. So if we simplify this, 250 times 1.03 to the t power. So what this is allowing us to do is, if you think about why it's 1 plus, if I took 250 times 1, it remains unchanged. But if I'm going to increase by 3%, I would have 250 times 0.03, and this would be the amount that I'm increasing. Sorry, have that typed in there correctly. So 250 times 0.03, this would be the amount that I increase, and I want to add that to the 250. And so we can account for that by taking 1 plus 0.03, or 1, and so the 250 times 1 plus the 250 times 0.03. Now, the reason that we do this to the t power is because we would have to repeat this process over and over again. So if this gives me my amount for year 2, I could then do this number, 257.5 times 1.03, and that would give me my value for my second, in this case, year. And then I'd repeat that process over and over. Or the number of times that we repeat the process could be represented as an exponent for time. So in this case, the equation that's going to represent the growth of the savings account over time is C, 250 times 1.03 to the t power. In problem number 2, it says, if the population of a town is decreasing by 4% per year and started with 12,500 residents, which of the following is its projected population in 10 years? And we want to show the exponential model we used to solve the problem. So we're going to go back to this equation because each year is going to be a percent of the previous year. It is decreasing by 4% per year. So we can start with Q of t being represented by the initial value, and the initial value was the 12,500 residents. This time the population is decreasing, so we are going to represent our model with 1 minus the rate that it's decreasing. So 1 minus 4% would be 1 minus 0.04, and to the t power. This equation would represent the decrease of the population over time. So again, why it's minus, if I were to take 12,500 times the percent, which is 0.04, this would be the amount that the population would decrease 1 year. So I would want to take the 12,500 minus this amount, 500, and this would give me the population at the end of the year. So we can account for that by taking 12,500 times 1 minus 12,500 times 0.04. And so our model then would, in this case, be simplified to 12,500 times 0.96 to the t power. So this is the model. Now what we're wanting to find is the population after 10 years, the projected population. So we don't know for sure if this is what it's going to be, but this is what we're going to assume the population will decrease to in 10 years. So the quantity after 10 years can be represented by taking Q of t. And we can do this algebraically quickly in the calculator. 12,500 times 0.96 to the 10th power. So Q of t would equal approximately 8,310.41 if we were to round to 2 decimals. But remember, in the case of our problem, it's population. You cannot have a portion of a person. So we're going to round to the nearest person. In this case, we can assume that approximately 8,310 people would remain in the town after 10 years. So again, this formula works when we are taking the quantity over time if we are increasing or decreasing by a percentage rate for a given amount of time consistently. Let's take a look at one more instance here, one more example problem. So I'm going to bring my formula over here so we can reference it. It says in problem number 3, the stock price of Wind Power Inc. is increasing at a rate of 4% per week. Its initial value is $20 per share. At the same time, the stock price in Gerbil Energy is crashing. It's losing its value at a rate of 11% per week. If its price was $120 per share when Wind Power was at $20, after how many weeks will the stock prices be the same? So in the first part, in part A, it says write exponential equations to model each function. So let's let W of t be wind power over time. So W of t, the value of its stock would be the initial value, which is $20, times 1 plus the rate that it's increasing. So it's increasing at 4%. So we do 1 plus 0.04, which would be 1.04 to the t power. In part B, or sorry, the second equation, still part A, but the second equation is for Gerbil Energy. Let's let that be G of t. G of t is going to be its initial value of $120 per share times 1 minus the 11% that it's decreasing. So 1 minus 0.11 would be 0.89 to the t power. So in both instances, we have functions that are increasing or decreasing at a percentage rate of the price the week before. And so here we have two equations to represent each of the two functions. Now in part B, we are asked to sketch and label a graph of the two functions. So I'm going to use a little color coding here. First, we want to get some axes. We know that the value of the stock could be positive or potentially negative. But we know that the weeks can only be positive, so I'm going to show quadrants 1 and 4 here. Potentially may not need quadrant 4, but just in case. And I'm going to label these axes. So the y-axis here is going to be the price per share, as the price is dependent on time. In this case, time is weeks. And so we can use the graphing calculator here to sketch out this equation or sketch out this scenario. So I can take my graphing calculator and input both equations using x as my variable for t. So I'm going to take a moment to make sure that we have these equations in here correctly. And then we can adjust the window. So I'm going to set the x minimum to 0. I'm going to set the x maximum to, let's say 52. Let's put it out for an entire year and see what happens here. And really what I'm looking for is when the price of the stocks will be the same. And so here we see the first curve represents the price of durable energy. The second price represents, wind power incorporated. The second price represents durable energy. And I can bring this down to the y minimum, to 0 to the x-axis. And we'll see that I don't actually need quadrant 4, so I'm going to shorten up my graph here. And I'm going to draw a sketch. So the green line coming in will be wind power. And I'm going to label these as well as my axes. Sorry, the green line is wind power. Wind power should look like this. I'm going to label these functions as well as my axes, just so that we can distinguish which function is which. So I color-coded my graph, but also want to make sure that I label my graph. Okay, so this is my sketch. It's not perfect, but it gives us a representation of the equations. So if I want to find the solution graphically, I want to find how many weeks or after how many weeks that the stock prices will be the same. I'm looking for the intersection place there. So I can find that intersection place using the second trace feature, making sure I select both curves. And here we have approximation. So we'll go ahead and round this to two decimals. And we can answer question B and say, after approximately 11.50, which is the x-axis here, which is our weeks, after approximately 11.50 weeks, the prices will be equal. So we had an increasing exponential representation of a curve, a decreasing exponential representation of a curve. We were able to develop both of those equations from our generic form here, substitute those into the calculator, graph, and find the intersection. So here is an application of some exponential growth and decay modeling. This is a good place to stop for today. As always, thank you guys for tuning in, and we'll see you soon.